Okay, so one other thing that we're going to talk about when we're thinking about heat and thinking about thermal energy is what we call heat capacity or specific heat. Often I will say, I'm going to try to say heat capacity because that's what the book uses, but I've always called it specific heat generally for myself. So if I say specific heat, I mean heat capacity is specific heat for our purposes in this class. So um, heat capacity is defined as the amount of heat, so the amount of energy you have to transfer into 1 gram of a substance to change the temperature of that substance by 1 degree, okay? So usually we measure this in joules. However, we could use any energy unit here that we wished. I mean, we could use any of these, but the point is that specific heat capacity compares an energy unit to an amount of mass and degrees Celsius. So that's kind of how it works here. So what is it telling us in the end? So what it's telling us is basically how easy it is to heat up 1 gram of the substance by 1 degree Celsius. So the higher the specific heat capacity, the larger that number is. That means you have to put more energy in to raise our substance, 1 gram of our substance by 1 degree Celsius. So if we have a really high specific heat, that means we have to put in a lot of energy to do it. So if we have a high specific heat, it means it takes a lot of energy to heat up our 1 gram by 1 degree. But if we have a low specific heat, we don't have to put in much energy to do that same process. So the higher the specific heat capacity, the more heat it takes to change the temperature. So if you think about it, if I just was getting ready to cook and I want to preheat my pan, right? I might just take my metal pan and set it on my stove. That metal pan heats up pretty quick, you know? If you got a gas flame on your metal stove, if I left that for 30 seconds, I walked up and touched it, I'm going to burn my hand right away. However, if I take my metal pan, I pour some water in it, and I'm heating water over a flame like that. If I walk up in 30 seconds and stick my finger in the water, I'm not going to burn myself if I directly touch the water. So it takes a lot more energy being transferred into that water than it does the metal of the pan. So, I mean, that's why we use metal pans, is because it transfers the heat very easy. But that's why it takes longer for your water to boil than it does for the metal to heat the pan. Or to heat the metal pan. So I thought I'd ask you guys a question here. So if you want to go ahead and pause the video and think about what's on the screen, I'll just explain the question a little bit, and then you can pause, choose what you need to do. So basically, we're thinking about the fact that the specific heat capacity of substance A is twice of that of substance B. So that means specific heat for the heat capacity of A is bigger than the heat capacity of B. So if I have the same amount of stuff, which substance can I get to a higher temperature? So I'm going to add the same amount of energy. I'm going to have the same amount of mass. The only thing that differs between A and B is the heat capacity. So if it has a higher heat capacity, can we get it to a larger temperature? Or if it has a lower heat capacity, could we get it to a higher temperature? So go ahead, think that guy through, and pause the video and come back when you're ready. The thing we're going to talk about is how energy and heat capacity relate to each other. So we can use the heat capacity in relation to the mass of the substance and the change in temperature to determine the amount of heat that's been transferred in a substance. So remember, heat is the transfer of thermal energy. So when we're measuring Q here, we're measuring how much heat is transferred in or out of our system as the process happens. So here's the equation that relates energy, thermal energy, Q, and heat capacity, mass, and temperature. So we call it Q equals MC delta T. I always learned it as Q equals MCAT. So that's an easy way to remember it too. But again, the Q stands for heat, M stands for the mass of the sample, and then the delta T means final temperature minus initial temperature. So where did the process end at and where did it start at? So just to be a little more clear, that delta in science and chemistry generally means change in. So you can read delta as the words change in when we're looking at this in chemistry. So really what we're saying is the heat, Q, equals the mass times the heat capacity, C, times the change in temperature. So I could say times the change in temperature. So that delta T, that delta anything, always means final value minus initial value, ending point minus starting point. So where you ended minus where you started. So we'll go ahead and work through some examples of how this works. And that's that. So that's going to be our information for Chapter 3. Remember, we worked all the way through matter, and now we're thinking about how matter and energy relate and how energy relates to some of the topics we've talked about. So see you later. Okay, so let's go ahead and work through some examples of how we can use specific heat and the mass of the sample and some information about the temperature change to find the heat. So my question here says, how much heat will I need to warm a 20-gram sample of water from 32 degrees Celsius to 50 degrees Celsius? And the heat capacity of water is given as 4.184 joules times grams degrees Celsius in the denominator there. So let's go ahead, first and foremost, pick apart what we know, what we're looking for, and we will go from there. So what information are we given in this question? Well, we're told we have a 20-gram sample of water, so we have 20.00 grams of water. We're told that we're going from 32 degrees Celsius to 50 degrees Celsius, so that means our starting temp is 32, and our ending temp is 50.00 degrees Celsius. So that's the information we're given. We're also told at the end of the problem what the specific heat of water is. So when we're calculating specific heat and we're looking at different kinds of samples, you either will be given the heat capacity or you should be able to kind of Google it and look it up. So if you're told that it's iron, for example, and you don't know what the specific heat capacity of iron is, you can just search that information. So in the end here, that's the information we're given. So we're also given that the heat capacity, which I'll call C, our symbol for heat capacity, 184 joules per grams degrees Celsius. So those are all kind of the numbers we can pick apart and pull out of our equation. And then we're wondering how much heat. So in the end, we want to know how much heat. Okay, well, I've given mass of a sample. I can see that I have some information about temperature change, and I've got information about a specific heat. We do have an equation to relate these values together. So I'm going to go ahead and write down our equation. Our equation is Q equals mc delta T. So when we're working through this, anytime we're thinking about heat and specific capacity, the mass of the sample, information like that, this bad boy, Q equals MCAT, is going to pop back up, okay? So basically from here on out, we just have to figure out how to plug these values into that equation, solve for heat. So I'm going to go ahead and I'm going to move over here so I have a little more space to work. And I'm going to plug into my equation. So my equation is Q equals mc delta T. All right, so heat, Q, is what we're looking for. So I'm going to say I have Q here. Mass, do I know that? Yep, my mass of my sample is 20.00. So I'll plug in my mass of my sample. I need more space. Times that specific heat capacity, which we know is 4.184 joules per grams degrees Celsius. And we're going to multiply that by our temperature here. So remember, delta T always means final minus initial. So end minus start. So our end is 50. So I'm going to take 50.00 degrees C minus
32.00 degrees C. And remember, I'm just multiplying all three of those numbers together. So where do we go from here? Well, let's do the math. So if I'm looking at Q, I'm going to have all the numbers, and I'm going to save the units for the end. By the way, we're going to do this problem because I want to make some points to us about the units, okay? So in the end here, we've got 20 grams times 4.184 joules divided by grams degrees Celsius times 50 minus 32. So when I plug all of this into my calculator, I plug my numbers in. I did 20 times 4.184 times 50 minus 32. I get 1506.24. So give me just a minute on the sig figs. We'll talk about the sig figs. However, let's talk about our units first. So if I'm looking at this, I have a grams from here. I have joules joules divided by grams degrees Celsius. So I could rewrite that so it looked like joules divided by grams degrees Celsius. And then when I subtract 2 units, the unit stays. So this has a unit of degrees Celsius because I'm just subtracting those 2. So unit of degrees Celsius. So I'm multiplying by degrees Celsius. So remember that grams is over 1. Degrees Celsius is divided by 1 as well. So it's kind of hard to see here the way I have it written, but I've got grams on top, grams on bottom, degrees Celsius on top, degrees Celsius on bottom. We're left with joules for our answer. So our answer in the end will go back to those proper significant figures. These two add and subtract, so they both have 2 decimal points, which means they have 4 significant figures when I multiply. So I've got 4 significant figures here, multiplication with 4 significant figures here. My answer gets 4 significant figures. So my answer in the end is 1,506 joules, because my 2 keeps my 6 the same when I'm rounding. So in the end, we were looking for how much heat we had. We figured out how much heat it was going to take to heat our 20-degree sample of water from 32 degrees Celsius to 50 degrees Celsius. Okay, so one last example here. We're going to work through another problem having to do with specific heat capacity, and then I'll leave it to you. So this problem says, if I add 32.4 joules of heat, to an unknown mass of iron, I am able to raise the temperature of that iron from 10 degrees Celsius to 20 degrees Celsius. If the heat capacity of iron is 0.4429 joules per grams degrees Celsius, what's the mass of the sample in the end? So let's figure out what we're given, figure out where we're going, and then we'll go from there. So the information that we're given in this problem, let's go through and pull all our different numbers. So it looks like we've got 32.4 joules of heat. We don't know the mass. I'm able to raise the temperature, so my temperature goes from 10 to 20. So my start point for temp is 10.0 degrees Celsius. My end point for temp is 20.0 degrees Celsius. And then it looks like I'm given the specific heat capacity of iron as well. So that would be C for heat capacity equals 0.449. And we're told the units on that are joules, grams, degrees Celsius. So joules divided by grams, degrees Celsius. And then in the end, we're looking for mass. It says how much mass. So basically, the way this kind of works, the experiment that I'm describing here is basically like, okay, you don't know how much iron you have, so you were able to measure how much heat you added to go from 10 to 20, so that information can give us the mass. So that's how this could be practical, right? I don't know how much iron I have, but I know how much heat I'm adding, I know what my temperature change is, I know the specific heat capacity of iron, boom, we can figure that mass out. So again, in the end, if we've got all of this information about temperature, mass, heat capacity, and Heat in general, we're going to use our Q equals mc delta T equation. Okay, so we're going to go ahead and figure out how to plug these values into our equation. So Q stands for heat. In this case, we're told that we have 32.4 joules of heat. We're looking for mass. We don't know mass, so we're still going to call it M. We know the heat capacity C. The heat capacity C of iron is 0.449, and then I'm going to rewrite my unit so that I have joules divided by grams Celsius in a more apparent manner there. I just made my fraction look better. And then I have my temperature change. So that's going to be our end point minus our starting point. So I'm going to actually put this down here on the second line. Same kind of multiplication as before. 20.0 degrees Celsius minus 10.0 degrees Celsius. So let's simplify this number first and see what we can do. So if I have 32.4 joules equals M times 0.449 joules divided by grams degrees Celsius. And then if I do this subtraction, I get 20.0 degrees Celsius minus 10 degrees Celsius. They both have 1 after the decimal point. So if I do that subtraction, I get 10.0 degrees Celsius, making sure I keep my significant figures correct. And then let's do some more simplification on this end to see what we can have happen over here. So I'm still going to stick with my 32.4 joules. I'm going to have my mass times something. So what I'm going to do here is rewrite this unit really quick. Degrees Celsius divided by 1. So if I'm looking at this, I'm going to go ahead and multiply these two numbers. So 0.449 times 10.0, that is going to give me 4.49 again. And then if I'm looking at my units here, I have grams Celsius, or I have degrees Celsius on top, degrees Celsius on bottom. I can get rid of that degrees Celsius. So I could say that on this side, I now have 4.49 joules divided by grams. I'll write that as the other pen fraction, sorry. Joules divided by grams. And then from here, we want to get M all by itself, so we're going to divide here. So I have divided by 4.49 joules divided by grams. And I have 4.49 joules divided by grams. In the end, this is the same on top and bottom, so I can get mass by itself. So I'm going to write mass on the right-hand side here for a second. I'm going to go ahead and do the math and then write the units out. So if I go ahead and I divide 32.4 divided by 4.49, I get 7.21, 60, and on. And then if I'm looking at my units, I have joules divided by grams. Remember when we see that unit where we have a small fraction and our big fraction, we can flip our little fraction and put it on top. So my unit would be joules times grams divided by joules. So this is again joules over 1. So I've got joules on top, joules on bottom cancels. And the way I can triple check that I have the correct unit is that I have mass here, and mass is being measured in grams. Checks out. So if I want to write my answer with proper significant figures and proper units, I go back to my problem as I've been working through. Heat capacity doesn't affect it. I figured out when I subtracted these two, I still had 3 significant figures. So 3 significant figures, 3 significant figures, answer gets 3. I have 7.2. My 6 is going to round my 1 to the number 2. So I have 7.22 grams is the mass of my sample in the end. So that's another way you can work through a specific heat capacity problem. So I might ask you for the temperature change. I might ask you for the mass. I might ask you to figure out the specific heat capacity if I don't give it to you and I give you all the other information. Or it might be like the first example where we figure out heat. So that's chapter 3.